Good. Thanks, Hanshwan, for the introduction. That's right. QIP is my favorite conference, and this is my 15th QIP in a row. So um, thanks to the steering committee for inviting me to give this tutorial. Thank you all for coming here. I know this is first thing in the morning, so I really appreciate you coming here instead of sleeping in. Okay, so I'm going to talk about quantum algorithms. This is the quantum algorithms tutorial. Feel free to ask questions. There's apparently microphones, and so someone will find you, and you can ask your questions. Okay, so yeah, as Antoine said, my name's Robin. I work at Google Quantum AI, and I'm going to be telling you about quantum algorithms. All right, so when I first started thinking about what I wanted to cover in this tutorial, it dawned on me that quantum algorithms is a vast, vast field, right? Like it's easily something that my clicker's not working. Nope, clicker's not working. Damn. I checked this before it started, but nope. Yeah, pointer's working, but I can't get the slides to move. Oh, there we go. Did that work? Okay, great. Yeah. Well, yeah, that's all I wanted to say. Yeah, quantum computing. So quantum algorithms is a vast field, and I thought maybe I'll maybe give you an overview of the field. So it's huge in the sense that you could easily do a 1 semester, 2 semester course. Maybe you can do a year-long course on quantum algorithms, and you probably still wouldn't touch everything that there is to cover in quantum algorithms. So at first I thought maybe I'll just give you an overview of the field, but then I realized that this was already done 3 years ago at QIP. There was a QIP 2021 tutorial by Andrew Childs, which gave a fantastic overview of the field. And the field hasn't changed that much in 3 years that like I would have significant new content. So I figured, let me try something else. But before I go on to what I want to talk about, let me give you resources for if you want just a good high-level overview of the field. There's the tutorial by Andrew Childs that I just mentioned from QIP 3 years ago. There's another tutorial by Andras Gillian from QIP 4 years ago. If one 3-hour tutorial at QIP was not enough, there's a second one. There's also a short survey by Ashley Montanaro, which is like about 10, 15 pages or so kind of the same level of, same high level as the tutorials. And if you're looking for something a little more in-depth, these are some recommendations. The first is lecture notes for a semester-long course by Andrew Childs. You can find it at this link. There's video lectures, again, for a semester-long course on quantum computing, but most of it is on quantum algorithms by Nathan Weeb. There's a very nice survey on quantum algorithms that just came out earlier, well, I was going to say earlier this year, but in 2024. So 3 months ago in October. And it's by the folks at AWS Quantum and collaborators, and it's kind of divided into 2 parts. There's the first part on applications and end-to-end complexities, and what they mean by this is fully fleshed out applications of quantum algorithms, not just abstract quantum algorithms where you need to plug in pieces, but like fully fleshed out quantum algorithms where you have a classical input, classical output, and this is a problem that somebody actually wants to solve. So the first part of the survey covers that. And the second part of the survey is just on primitives used in quantum computing, quantum algorithms. So things like phase estimation and so on, which is really nice. So I recommend reading the survey as well. And finally, there's a quantum algorithm zoo. This isn't like a textbook. It's more like an encyclopedia. It's a list of the known quantum algorithms. So you would go there if you want to look something up. Not really something I would recommend reading from like cover to cover. Okay, good. So that's general resources on quantum algorithms. So what do I want to talk about? So instead of just surveying the field, I thought I'll do something slightly different. And that is, I'll talk about how to design new quantum algorithms, or in other words, how to be a quantum algorithms researcher. I don't know, that's the title. Or maybe one way to think about it is just like if I could go back in time and tell myself when I was a graduate student, like what do you need to know to do quantum algorithms research? Like this is what I would tell myself. Of course, some of the stuff I'm talking about right now didn't exist 15 years ago, but yeah, you know what I mean. And so yeah, so it's just my perspective, and this is so I wanted to emphasize just my biased perspective on this. As it's just one computer science perspective. You ask a different person, they might have a different perspective, and there's certainly no right or wrong answer. It's not the kind of thing that there's like covered in a textbook of like, this is how you become an algorithms researcher. So, well, I hope you get something out of it. And if not, there's those other resources I talked about. You can watch Andrew Childs' tutorial from 3 years ago. All right, cool. So yeah, so how do you design new quantum algorithms? And here's the answer. It's, oh, there we go. It's the same way we design new classical algorithms. And that's cool. That's all I wanted to say, and that's the end of my talk. Thank you for coming. Cool. Okay. Okay, this actually worked. Cool. So this isn't just a joke. I think, like, to be really successful as a quantum algorithm developer, you should have a strong foundation in classical algorithms, because it's kind of just more of the same. It's more algorithms. You change the model a little bit. Sure, you went from classical to quantum, but like the core thing that will help you be successful, I think, is to understand classical algorithms. And in fact, this joke here is in fact an example of a classical technique called a reduction, where you reduce an existing problem to a known solved problem, which is the problem of designing classical algorithms. In fact, that problem is also not totally solved. And if you ask a classical algorithms researcher, how do you come up with new algorithms? It's everybody will have their own opinion and so on. And I'll tell you my point of view, which works equally well for classical algorithms. It's not specific to quantum algorithms, but of course, my tutorial is going to be on quantum algorithms. But my perspective is the way you become an algorithm designer, or way you become good at designing new quantum algorithms, is by understanding the building blocks of algorithms. Not just understanding as many different algorithms as you can, but understand the pieces that make up algorithms. And the reason I like to say this is that you can think of an algorithm's like a pizza. So feel free to quote me out of context on that. An algorithm is a pizza. And it's like this. Have you ever been to a pizza place that allows you to make your own pizza, and maybe they give you 3 choices for the crust and 4 choices for the sauce, and like 10 toppings choices. And how many possible pizzas can you make? You can make a lot of pizzas, right? You can choose any crust you want, any sauce you want, and like any subset of the toppings. That's like that many number of pizzas. I don't even know what that is. Like, it's in the millions of pizzas, right? So of course a pizza place is not going to list out all possible pizzas that you can make, right? That would be insane. They'll just tell you the building blocks, right? Like what they can make a pizza out of. And once you understand this, you know all the pizzas you can make at this place. And that's kind of what algorithms is all about. There's these little building blocks that we use, which are like the paradigms of designing algorithms, things like divide and conquer and dynamic programming. There's like the primitives of algorithms, like little subroutines that you'll use over and over again, like binary searching through something. And if you understand these things, and little tricks, which you kind of just learn with experience, they often just don't even have names. They're just like little tricks you pick up. If you know these building blocks, it'll be much easier to understand new algorithms. It'll be much easier to design new algorithms. And that's kind of what I want to promote in this talk today. And I want to tell you about these building blocks of quantum algorithms. Okay, so so why am I talking so much about building blocks? Imagine if you looked up a recipe for a PB&J sandwich. So this is a sandwich. For those of you who don't know, it's just a sandwich. It has peanut butter, jam, bread. That's it. And you looked up a recipe online, and it was like super long. It was like 30 lines explaining how to make the sandwich, and you'd be like, wait, what's going on? And then you start reading this explanation, and then you're like, oh, okay, the first 15 lines are explaining how to make bread, and the next 10 lines are explaining how to make jam, and you're like, wait, I don't need to know how to make a PB&J sandwich at this level of detail. Like, I want you to tell me just in terms of the building blocks, which is like, in terms of bread, I'll figure out how to make bread. If I don't know how to make bread, I'll look it up, or I'll just go buy it from the store. Just like in algorithm design, we want to tell you stuff at the right level of generality, right? Like in terms of the building blocks, not all the way in terms of like the most primitive elements of your whatever it is, let's say programming language. So just to give a programming analogy, let's say I'm giving you a classical algorithm just for this problem called threesum. It's a famous problem studied in classical algorithms. Here you're given 3 numbers, and you asked, you're not given 3 numbers, you're given n numbers, and you asked if any 3 of them sum to 0. So you're given a list of n numbers. And let's say you read some code for this algorithm, and it was like 30 lines of, in whatever your programming language we're talking about, let's say C++. It's 30 lines of C++ code, and it's like, there's a lot of for loops and whatever, and you're like, oh, this is like, I don't know what's going on. But then if somebody just tells you what are the building blocks involved, which is just like, okay, the first part of the code is sorting the numbers. The second part of the code is brute forcing over all pairs and choose 2 pairs. And the third part is just binary searching for a third one, so to check if they sum to 0. This is a much more understandable way of explaining an algorithm, right? Like, you probably wouldn't prefer it if I gave you 30 lines of C++ code. And these are the building blocks, things like sorting and binary search. These are classical building blocks, but what I'm saying is this is the kind of stuff that's important to know to understand how to design new algorithms, either classically or quantumly. And so what kind of building blocks do you need to know? Okay, so hopefully maybe I've convinced you that we need to understand these building blocks. But what do we need to know? So I like to think of quantum algorithms this way as 2 generalizations away from classical deterministic algorithms. So deterministic algorithms are usually the algorithms you learn in any introduction to algorithms class, which is just classical algorithms on a classical computer that always have to get the answer correct. They have no access to randomness. They don't make any errors at the end of the day. Randomized algorithms are a generalization of this, where you get access to randomness, and then you're also allowed to get the answer wrong at the end of the day, similar to quantum algorithms. And then a further generalization of this is now you also, in addition to using randomness, you can use quantumness. So you can use the power of quantum computers. And these are all proper generalizations in the sense that a quantum algorithm can always mimic a randomized algorithm. A randomized algorithm can always mimic a deterministic algorithm. So if you're designing a deterministic algorithm, you'll use building blocks, as I said before, but you'll only use building blocks that are deterministic in nature. So there are building blocks that work for deterministic algorithms, and that's what a deterministic algorithm will look like. It'll be made of these little building blocks. I'm using these little Lego pieces to indicate, to these building blocks. So that's a deterministic algorithm made out of building blocks. I'm going to use red for deterministic building blocks. And okay, now let's say you're trying to build a randomized algorithm. What is it going to be built out of? It's not going to be built out of just randomized building blocks, because you can also use deterministic building blocks, because as I said, a randomized algorithm is a generalization of a deterministic algorithm. So you can always use deterministic blocks. So it's like a Lego piece where now you get two colors, right? So you get the black color for randomized algorithms, and you get the red from deterministic algorithms. So now you can make a richer class of algorithms, right? But also conversely, you need to know more building blocks. So if you're a randomized algorithm developer, you need to know all the bag of tricks that a deterministic algorithms person knows, and you need to know these new extra black colored Lego blocks. And the same thing's going to happen for quantum. Now there's a third color involved. There we go. And now you have these quantum blocks, which are depicted in yellow, and you can make even more interesting things. As you can tell from these slides, I'm a cat person, not a dog person. That's the more complex and interesting creature over there. So the downside is, as a quantum algorithms developer, you now need to learn three types of building blocks. You need to understand how these deterministic building blocks, randomized building blocks, quantum building blocks. And I'm going to tell you a little bit about these in this talk. Okay, cool. So I've been talking about these building blocks kind of abstractly. I just want to give you some examples of these building blocks. But before I get to that, I just want to say the reason why I'm emphasizing that even as a quantum algorithms person, you need to know classical building blocks is because otherwise what will happen is you'll keep rediscovering classical building blocks while designing quantum algorithms. This happens all the time. I think it's kind of a shame because it's a huge waste of time, right? Like you're working on your quantum algorithm and like you spend many hours and you're like, I just reinvented binary search. And you're like, well, maybe, this was easy stuff. Like you could have just looked it up. I mean, you waste a lot of time if you don't have the right background. Okay, so just I've been talking about these building blocks kind of abstractly. Let me just give you some examples. And okay, this is a huge list. I don't want you to read all of this, but just so you get a sense of like what I mean by building blocks, these are some examples of classical building blocks. So I'm using classical building blocks just because these might be more familiar if you've seen them before. And I'm roughly dividing building blocks into two types, what I'm calling paradigms. These are like frameworks for designing algorithms, things you might say like, you might say this algorithm uses the divide and conquer framework, or this algorithm uses dynamic programming, that kind of thing. If you've done like a programming interview at a company before, then you've probably been asked some of these like difficult dynamic programming questions, and it's a classic interview question. So it's a way of designing an algorithm is kind of what I mean by paradigms. And by primitives, I mean like little smaller things like subroutines, like tricks like binary search or sorting your numbers and so on. And I'm going to talk about many of these in the talk, but just wanted to put up some examples of what I mean by building blocks. So this is the kind of stuff that I feel is important to know. Okay, yeah. So why do I think it's important to know these primitives, the stuff I was talking about? It's because in my experience, this is kind of how an algorithm design journey looks like. There's some problem that you set out to solve. This is this big blue circle on the right. And then there's like the set of problems that you know how to solve. Like this is just the stuff you know how to do. And what generally ends up happening, at least in my experience, is you start out by trying to make progress either from the left or right. So maybe you start trying to make progress from the left, and you knew how to solve some standard problems. You've extended the space of problems you know how to solve by a little bit by using some known primitive. Like just use one of these tricks, bag of tricks that I was talking about for the previous slide. You go a little further, and then maybe you go a little further, and then you feel like you're making progress towards the problem you solved. But then maybe you got stuck, and then you're like, okay, let me try something else, and then you try something else, and again you move further to an intermediate problem, and then maybe you got stuck on that side, and you're like, you know what? Let me go backwards. So I have a problem that I want to solve. Let me try to see if there's a simpler problem that I can solve, which I can then get to the problem I do want to solve using an existing primitive. So you might say something like, let's take the problem I want to solve and let's consider a special case. Let's consider the special case where something is set to 1 or so some quantity is bounded. And then you show through some existing primitive that, oh, actually that's fine. That special case did indeed capture the full generality of the general case, and I just need to use some classic tricks. So for example, the problem you want to solve might be some problem where you have to output some number. And then you might take the special case of just solving some decision problem of is this number bigger than something or smaller than something? And you can go from one to the other using binary search. This is a classic primitive that lets you upgrade a decision task to a search task. So you might do this, and then like this is kind of how algorithm design works in my head. You keep doing this, you make the problem simpler, you start making progress further, and like often you're using just known primitives, and finally there's some place where you come up with something new that had to be developed, a new algorithm that you came up with. So if you didn't know all of these primitives, it would be very hard to go from the space of stuff you know to the space of stuff to the problem that you actually want to solve. And in fact, when you see a quantum algorithms paper, or just a classical algorithms paper, you'll see even though the algorithm is pretty long, a lot of it is just known stuff. That's just known primitives. That's the building blocks. And then there'll be some part that's the new part. And if you're not experienced enough in the field, you'll not be able to understand what if this paper is like the new stuff and what's the old stuff. Hopefully the paper is written clearly enough that they explain this is all known stuff, this is primitive stuff, and this is our new contribution. But if you just see an algorithm written, like if you see source code in C++ or something, it will be completely unclear, like what's totally standard stuff and uninteresting and what is the new contribution. But often this is how algorithms papers go in my experience anyway. So this is why I'm saying, yeah, learn the primitives. Don't focus on learning all the possible quantum algorithms out there. That's just going to be a fool's errand. So yeah, hopefully this is captured by this meme. That's my cat, Ted. And he's saying, knowing more algorithms, he doesn't care. He's not excited. But knowing more primitives, now he's listening. Okay, so this is the message I want to take away. Learn the primitives. Okay, good. So once, let's say, so yeah, why should we learn these primitives? I hope I've made this I don't know, previous few slides have made this thesis clear. But one actual way of designing a quantum algorithm is you start out with a classical algorithm, and you look at all the pieces of this classical algorithm, and you try to upgrade the pieces that can be made quantum. So I'm saying upgrade as into to lift a classical building block to a quantum building block and get a speed up. And so I'm going to call this quantizing a building block. And let me give you some examples. So let's say you look at a classical algorithm, and you observe that it's doing some kind of brute force search over a set, and it's checking some property of every element in some set. And then you might ask yourself, could we Grover search over this set instead? And if you can, then that's, you get a quadratic speed up for free. So that's pretty cool. So for example, the algorithm I was talking about a couple of slides ago, there was a brute force step. You can actually Grover search that and speed up that algorithm. So this works. You can often take a good classical algorithm, just take little pieces, make them quantum, and get a better quantum algorithm. Another example would be you see a classical algorithm, it uses a random walk, and you might think, can I use a quantum walk? Maybe you can. So that's the kind of stuff you can try when you're trying to upgrade a classical algorithm to a quantum algorithm. So my takeaway message from all of this stuff is, even if you're a quantum algorithms developer, you need to understand classical building blocks, because A, you might just want to use them directly in your algorithm. As I was saying, you saw this picture of this Lego cat. It wasn't only using quantum building blocks, it was also using classical building blocks. So you might want to know them just to use, or you might want to know that because you might want to upgrade a building block to a quantum building block. So it's important to know classical building blocks. It's also important to know which ones of them can be upgraded. So you have a sense of when you see an algorithm and you're like, oh, this piece can probably be made quantum, and I'll get a speed up if I run this on a quantum computer. So that's kind of what I'm going to talk about today. I'm going to talk about some classical building blocks, and I'm going to comment on which ones can be made quantum, which ones can be done faster on a quantum computer. And okay, so that's the first part of my talk, the intro. And this is kind of going to be the outline of the talk. I'm going to tell you about classical paradigms for building classical algorithms that can be quantized or can be upgraded. We're going to work through an example, so just to make things a little more concrete. I'm going to have to take a little detour into random access models because some of the later stuff will need that. Then I'll talk about query complexity, or having access to inputs through queries, which is a pretty big part of quantum algorithm design, even more so than it is of classical algorithm design. And then in the second half of my talk, I'll talk about classical primitives that can be quantized. So again, like before, I was talking about classical paradigms, which can be upgraded to quantum paradigms. Same thing, but for primitives, which, as I said, I'm dividing the building blocks into like two things: frameworks or paradigms, or subroutines or primitives. Then I'll talk about some primitives that are just natively quantum. Like, it's not really fruitful to think of them as being upgrades of a classical primitive. They're just quantum algorithm design primitives. I'll end with a summary, and then I'll tell you a little bit about, or at least I'll just give you a bird's eye view of all the quantum algorithms talk at QIP. So if you're excited after listening to this tutorial and you want to go and learn quantum algorithms at QIP, then you should go to all of these talks. Actually, some of them are happening simultaneously. So you can't go to all of them, but you can try to go to some of them. Okay, good. So that's the first intro part of my talk, and now I'll tell you about quantizable classical paradigms. Maybe let me pause for questions if there's any. This was just really high-level stuff, so maybe there's no real questions about this, but just to make the point that I do promote people asking me questions, I'm going to pause here. Nope. Okay. Okay, good.
Are there known cases where you can provably say that there, like this primitive compartment that's classical cannot be quantized?
Right. Yes. So the question was, are there known cases where you can prove that a given classical primitive cannot be made quantum? Yes, there are. And when I come to the section on quantizable classical primitives, I'll give you examples of both primitives that can be upgraded and primitives that provably cannot be upgraded to the quantum world. So you'll see some examples. Good question. Okay, so as I was saying earlier, most of my talk will be about these primitives, these tools, techniques, subroutines, tricks, whatever you want to call them. But just before getting to that, I want to talk about these paradigms, these overarching ways of designing algorithms that are very popular classically, and which ones can be upgraded to a quantum primitive. I won't spend too much time on this, just it's mostly pointers if you want to go learn more about these things yourself. So let's start with divide and conquer. If you've taken an algorithms course, this is like one of the first primitives we teach classical algorithm students. There is kind of a quantum generalization of divide and conquer. It works in some cases. And in fact, there's a talk. So talks in blue will be talks at this QIP. So in fact, there's a talk on Monday that you can go, and it's called On the Quantum Time Complexity of Divide and Conquer. So if you want to learn more about divide and conquer, you can go to that talk. Dynamic programming, this is another classic algorithms design paradigm. There are some quantum speedups. Again, it's not like you can always speed up a dynamic programming algorithm. In fact, this is a big open question, but sometimes you can, and this is an example of a situation where you can. Then there's the brute force paradigm, which is just you brute force over some solution space, and as I was saying, you can try to see if you can do Grover instead of that. That often works. Notice there's no citation for Grover's algorithm because it's so famous that you don't need to cite Grover's algorithm. Like that's the dream of any algorithms designer, to get up there that your algorithm can you just say the name of the algorithm. Nobody even gives a citation. That's the dream. Okay. Okay. More paradigms. Let's talk about backtracking and branch and bound are two classical algorithm design paradigms that are often used for combinatorial optimization. There are pretty generic quadratic speedups for both of these. And here are some references for those. I should say, for some of these things I give one citation, and for some I give two. When I'm giving two, usually the first one is the oldest work that I know, or maybe the work that started this thing, and the second one is usually the newest work that I know, or the best version of that algorithm. So feel free to look at either of them if you want to do a proper literature search. You can look at the citations of the newer one. That's usually one way to do it. Or you take the older one and look at articles that cite that article in Google search and Google Scholar. So that's a tip for people doing literature searches. That's how you find stuff. Either look at article citing or look at the references. Okay, so those are two classical paradigms. Greedy algorithms, I thought about this a bit, and a greedy algorithm looks like this. It's you have some space of possible things you can do, and just at every step you locally pick the best thing you can do and keep going this way. That doesn't always give you the correct answer, the best answer, but sometimes it does. So I think sometimes you might be able to use Grover to speed up the first part of the algorithm, the one that says that pick the best current move that you can make among the moves possible. But there's the other part, which is that you sequentially, adaptively keep picking moves one after the other. I think there's no quantum speedup for that part. And in fact, if you view the gradient descent algorithm as a greedy algorithm, because it's also kind of doing this thing where at every point in time, it locally chooses the best direction to walk in and it walks in that direction. So if you think of that as a greedy algorithm, in fact, there's no-go results that say that you can't speed up gradient descent. And in fact, there's one at this QIP, which is on Wednesday. So if you're interested in learning more about that, go to that talk. Right, now we come to the convex optimization primitives paradigms of classical algorithms. So there's the linear system solving idea, which is you reduce your problem to a linear system of equations. There is indeed a quantum algorithm mixed speedup for this problem, and I'll spend some time talking about this. There's linear programming or semi-indefinite programming, also a classic algorithm paradigm where you try to reduce your problem to one of these classic problems, both of which can be solved in polynomial time on a classical computer, and they can be solved even faster on a quantum computer. There is a talk at this QIP about this on Wednesday. Convex programming is a generalization of both of these. There are some quantum speedups for convex programming. These are papers you can look at if you want to know more. And my final set of paradigms I want to talk about is random walks. Now, this is actually the quantum version of this. Quantum walks is a hugely successful algorithmic design paradigm. So if I had to say out of all of these design paradigms, which one's the most successful quantumly, it would be this one, quantum walks. And so that's why I've given you a bunch of citations, because it's absolutely vast. The first exponential speedup that I know through quantum walks that uses a continuous time quantum walk is this QIP 2003 paper. So that's a good place to look if you want to understand continuous time quantum walks. If you want to understand discrete time quantum walks, there's the next two papers, the one by Ambainis and Segedi. If you want a nice survey on quantum algorithms, there's one by Mikler-Santha. It's quantum walk search-based algorithms. They're discrete time quantum walk algorithms that help you solve search problems. And if you want just a survey on just the entire field of quantum walks, both discrete time and quantum walks and continuous time, then I'd recommend the survey from 2012, which is a pretty in-depth survey. I think it's like over 100 pages survey just on quantum walks. Okay, and another popular paradigm classically is the Monte Carlo method. This is like actually a very old algorithmic technique, like over 100 years old. And there are quantum analogs of this that give you generic speedups. Generally, you get a quadratic speedup over whatever your classical complexity was. And simulated annealing is also a classical algorithmic paradigm which can be sped up. You can view it as a special case of the previous two, but I just thought I'll call it out separately. And this is one paper you can look at if you want to understand more. And that brings me to the end of my paradigms. I think that's right. Okay, good. So this was just some classical paradigms that you can speed up on a quantum computer. I didn't really explain any of them in detail. This was just like references for you to look at if you want to go learn more about them. And just so you have a kind of bird's eye view of what kind of classical algorithmic paradigms can be upgraded to quantum paradigms. What I really want to talk about is some examples and primitives, these little tools, techniques, tricks that you can use to design your quantum algorithms. Okay, yeah, so again, before getting to that, maybe this is a good time to pause for questions. Any questions?
Just curiosity, you've talked about primitives and paradigms, and I'm not a type theorist, but would it be interesting to think about something like types in quantum systems in terms of algorithm design, or at least in checking that what you're doing makes sense? I never hear people talk about it, but it is a big part of classical computer science.
I don't know. I'm also not a type theorist, and I'm also not very familiar with this area of classical computer science. But so yeah, I don't know. Any other questions? There's one over there.
Could you talk a little bit more on the no-go result that you mentioned on speeding up, on the quantum speedups for greedy algorithms?
Oh, the quantum speedup for greedy algorithms. Right. So yeah, as far as I know, I don't know if there's any general work on greedy algorithms. All I know is that if you want to think of gradient descent as an example of a greedy algorithm, you can't speed up gradient descent. And there's an older work that I cited on that slide, which I could probably go back. Yeah, which you can look at from QIP a couple of years ago, or there's work at this QIP. So actually, I recommend going to that. Well, because it's going to be a 30-minute talk, and hopefully it'll explain all the context and why. So as far as I understand, this paper shows that basically for this problem of finding stationary points of non-convex functions, which is a problem that you can classically solve with gradient descent, quantum algorithms don't give you any speed up whatsoever. And the previous work proved something similar, but that's for convex optimization. This is for non-convex optimization. In both cases, there's no speed up whatsoever for this adaptive part of gradient descent, the part that says that now I'll choose the best place to go from where I am now, and then I'll choose the next best place. At every step, you keep making this locally best choice. This part of gradient descent cannot be sped up. There's another part of gradient descent, which is how do you compute gradients from functions, which you may or may not be able to speed up depending on the computational model you're working in. But this part, there's no speed up for. So yeah, I'd suggest going to this talk on Wednesday if you want to know more. Oh, okay, good. Oh, yeah, your mic's not on.
Yeah, given the overview that you have shown, and I like the overview of your talk, and looking forward to it. Do you have also interest in this quantum machine learning algorithms? Is it a way to quantize them as well and to measure the advantage that comes from them? we talk about quantum machine learning algorithms, quantum generative AI, or something like that. Do you also will talk about that, or you have interest on those type of algorithms? Thank you.
Right. Right. So the question was about quantum machine learning. So yeah. So as I said, instead of like overviewing the field as like this is different topics on which quantum algorithms can give you speedups, I'm kind of doing a different way, which is like I'm going to talk about the primitives, and you can use them wherever you feel like. So I won't talk about any specific area like quantum algorithms for algebraic problems or factoring or for machine learning but I'm just talking about these little building blocks. So I won't actually talk about machine learning or any specific area for that matter. But many of these building blocks will be used in, well, pretty much every area of quantum algorithms. If you read quantum machine learning papers, they will have some of the building blocks that I'll talk about in this talk, for sure. If they don't, then it's a little sus. Like, are they really quantum algorithms if they're not using these quantum building blocks? Okay. Okay. Good.
Hello.
Okay, let's take one last question.
Yeah, I have a quick question. So for some of these primitives and algorithms, the output is like a quantum wave function, right? And like you can't directly put that into a classical computer. So like, which of these algorithms, like, can you directly put the output into a classical computer, and which can you not?
Good question. So these paradigms. So the good thing about these paradigms is they're just like ways of designing algorithms. So they're not even at the level of being subroutines that accept input and output. They're just like a framework for designing algorithms. So for all of the stuff I talked about so far, you don't have to worry about what the input and output models are. When I get to primitives, I will spend quite a bit of time talking about being very formal about like what is the input model? Is it a quantum state? Is it a classical bit string? What's the output? Is it a quantum state? And how do you compare this to classical algorithm? So I'll talk about that in some detail when I get to the primitives part of the talk. Yeah. Good question. Yeah. Okay, cool. So yeah, this is just overview of some paradigms, and now okay, yeah. So this is all like really high level stuff. So now let's like get our hands dirty. Talk about an actual example. Talk about some numbers. Talk about some asymptotic scalings. And let me just start by defining the quantum circuit model. So I should have said this earlier, but I'm assuming that the background I'm assuming from the audience is that everyone has kind of taken a first course in quantum algorithms. So you've seen quantum circuits before. You've probably seen Grover's algorithm before. You don't need to have seen all the latest and greatest quantum algorithms before. Just like an intro to quantum computing, so you know what a quantum circuit is and so on. So this is a recap. I'm not hoping to convey how quantum circuits work during this tutorial. Okay, so quantum circuits are built out of elementary gates from some universal gate set. And this is an example of a universal gate set that consists of 3 gates: the Hadamard gate, the T gate, and the C naught gate. You can build any unitary you want out of these, approximately. And when I give you a quantum circuit, the cost of the quantum circuit, or the complexity measure that we associate with quantum circuits most commonly, which is like how complicated is your quantum algorithm, is just the total number of gates. This is the most common thing to study. Certainly not the only thing to study. One other popular measure that I'll just mention is that for early fault-tolerant algorithms, people like to study a different gate set, which is the gate set of Clifford gates plus T gates, and they like to count only the number of T gates, because in these fault-tolerant architectures, T gates will be way more expensive than Clifford gates. So that's, for example, a different cost metric you could put on quantum circuits, but I'm just going to talk about total number of gates, because it's simple, it's nice, it's clean, it's also what's done classically. And if you have a quantum circuit that outputs is outputting a classical output, let's say even a 1-bit output, the traditional thing to do is you measure the first qubit of your quantum circuit, and output the measurement outcome. If it's 0 or 1, that's the classical answer of your quantum circuit. Okay, so so this is just a recap. Hopefully everyone has seen the quantum circuit model before. And let's take an example of a problem. So in fact, let's start with Grover's algorithm. In fact, so as I said before, there's a lot of primitives. Grover's algorithm maybe is one of the most fundamental primitives. We always teach it in an intro to quantum course usually. I hope everyone has seen this before, but I'll just do a recap. I'm not going to explain how Grover's algorithm works, but I'll just tell you what Grover's algorithm does. So in Grover's algorithm, you're given some unitary, OY, that is encoding a classical string y of length n. And it's encoding it in the following sense, that this is the behavior of the unitary OY on basis states of the form I comma b. I is some number between 1 and n, and b is a bit. It's either 0 or 1. And what you should think of the input as saying is that you're asking the oracle for what is the ith bit of my string y. So you're trying to learn yi by applying this unitary OY on IB. And what it does is this unitary, it leaves the first register alone. It just keeps it as I. And in the second register, it XORs the value of yi. So now if you read the second register, now you know what yi is. It's whatever b was XORed with the actual value of yi. The reason we do it this way is because we want a reversible unitary map that reads this data y. And that's what, and you can check that OY is indeed a unitary. So this is the input that's assumed for Grover's algorithm. And the goal is to decide, or like, what is the problem that Grover's algorithm solves? Grover's algorithm solves the following problem. It decides if y is the all zero string or if y is not the all zero string. These are the only two possibilities. Either it's the all zero string or it's not. In the second case, of course, that means there's some bit that's 1. So Grover's algorithm can solve this problem for you. And what is the complexity of Grover's algorithm? Like how much time, how much resources does Grover's algorithm take to solve this problem? Grover's algorithm will give you a quantum circuit that solves this problem with high probability. And so throughout this talk, when I say with high probability, I mean with probability at least 2/3. So, you know, it's decent probability. Maybe it's not super high, but I'll tell you later about why this doesn't really matter, this number 2/3. And what Grover's algorithm does is it uses this unitary OY some number of times, root n times. And in addition to this unitary, this OY that we've assumed as input, it also uses an additional number of elementary gates. You know, gates from our gate set that we talked about, this Hadamard TC naught or whatever your favorite gate set is. And the number of elementary gates it uses is root n log n. So what I mean is the Grover's algorithm will look something like this. It'll have these little black boxes. These are the elementary gates from your gate set. And it'll make uses of this big OY that we've assumed. So as stated, Grover's algorithm doesn't give you a legitimate quantum circuit to solve the problem because it has these big black boxes that are not elementary gates. So, you know, recall from the previous slide, the quantum circuit model only has elementary gates in it. It has these big black boxes. You have to replace them with actual quantum circuits to get a quantum circuit at the end of the day, right? So that's why Grover's algorithm is often called a black box algorithm or a query algorithm. And in fact, this is the field of query complexity. This is usually the first algorithm we might talk if we're talking about quantum query complexity. And I just want to say that don't be confused. Sometimes Grover's algorithm is presented slightly differently. It's the exact same thing. It's just a change of variables. So sometimes instead of saying you have access to an n-bit string, you might say you have access to a function that goes from 0,1 to the n to 0,1. And it's the same kind of oracle behavior. But you know, you usually think of strings and functions as different things, but they're actually the same thing here because you just think of the string y as the truth table of f, which is just the evaluation of f at every possible input. And so, and set capital N to be 2 to the little n. It's the same thing. So just don't be confused. Often you'll see Grover presented as searching for deciding if a string is all zeros or not, or deciding if a function is identically the zero function, or if there's some input on which the function accepts. So it's the same thing. Okay, so when you have this kind of access to a string, as I said before, we call this having quantum query access to the string, or quantum black box access. Black box because you're just assuming there's some OY which has this functionality. You don't ask any questions about what's going on inside OY. It's a black box to you as far as you're concerned. You only know about the input-output functionality of this black box. Okay, good. So Grover's algorithm is, maybe if I had to teach you one quantum primitive, this is the one I would choose. And now let me tell you how to use Grover's algorithm. There's a question there. Do you want
to? So one thing they usually don't mention in classical algorithm classes is this black box model. Like the first time you hear about the black box model is when you're learning about quantum algorithms. Is there a reason why classical courses don't really address the black box query model?
That is a very good question. Right, so the question is, why don't we learn about the black box model classically? Well, I think firstly, this is a shortcoming of classical algorithms courses. We should talk about the black box model. Query complexity is a fascinating and wonderful field, and everyone should study it. But I think the main reason why it's more popular in quantum is most of the quantum algorithms are just very naturally phrased as black box algorithms. So not just Grover's algorithm, but in fact, most quantum algorithms, you know, including Shor's algorithm, which we don't think of as a black box algorithm, it just takes a number and factors it, but inside it is hiding a black box speedup for this period finding problem. And that's really the only quantum part of the algorithm. The rest of it is just classical stuff. And many other algorithms that you might be familiar with, especially stuff I'll cover later on, phase estimation, Hamiltonian simulation, all of these you can think of as black box algorithms. So this way of looking at the input as a black box is just very fruitful quantumly. Classically, it's not as fruitful, but certainly you can think of many classical algorithms also as doing black box stuff. People just don't say it that way. They'll often instantiate the black box and give you the in my view, less abstract version of the problem with more concrete implementation details, which I think should be abstracted away, and people should talk about black boxes, but they don't. So maybe it's a historical accent, might be the way to put it, but it's just more useful quantumly is maybe the true reason why we always talk about it quantumly.
Thanks.
Yeah, good question. Good. So this is Grover's algorithm, and let me show you how to apply Grover's algorithm. Like, how do you get an actual speed up from Grover's algorithm, right? So as I said right now, this is still not a quantum circuit. It's this black box model stuff that we've been talking about. So let's take a problem that Grover's algorithm speeds up, and let's take this famous problem from classical computer science. It's called circuit SAT. This is very similar to the 3-SAT problem, if people have heard of this problem, which is where you're given a special kind of formula, and if you're asked if there exists an input that satisfies the formula. So here it's a little more general. You're just given a classical circuit. So a classical circuit is like a quantum circuit, except it has classical gates in it. So it has these and, or, and not gates, these Boolean logic gates. And it's a polynomial-sized circuit, and it computes some Boolean function f, and you're asked if this function is satisfiable, which means, is there an input x such that f of x equals 1? That's what it means for a function to be satisfiable. Cool. Before getting to quantum algorithms, let's just think about how would you solve this problem classically. Right? So you have some circuit. You want to know, is there any input that makes it evaluate to 1? What's the most straightforward algorithm you can come up with? I give you a circuit. You want to know, is there any input that makes it evaluate to 1? You could just try all inputs. Like that's certainly one thing you can do. It's kind of a naive algorithm, but certainly that's something you can do. Just enumerate every input. And how much time will this take? How many inputs are there? So how many strings are there of length n? There's 2 to the n such strings. So it'll take 2 to the n time per input. And for every input, you're going to run a circuit of size polynomial in n. So it's going to take 2 to the n poly n time. And despite this being a pretty simple algorithm, this is essentially the best algorithm we know. And it's widely believed that you can't really do better than this for this problem. You cannot do like 2 to the 0.999n, let's say. So you cannot go under 2 to the n is the I'd say prevailing belief among complexity theorists. Maybe there's some who disagree, but and if you want to know more about this assumption, it's often called the strong exponential time hypothesis, SETH. But anyway, the takeaway is there's this problem. You can solve it classically in time 2 to the n, and it is widely believed that it needs time 2 to the n. Okay, now let's solve this on a quantum computer. How do we do that? So step 1, let's start with the circuit we were given. We were given a classical circuit for this function, right? We want to use it in a quantum algorithm, so now we need a quantum circuit. So the first step is to actually take this classical circuit f that you were given and convert it to this OF type object that Grover's algorithm needs that we talked about earlier. Right, and can you do this? Like, you weren't given this object, right? You were just given a classical circuit. It had Boolean logic gates and or not, and you're requiring some kind of quantum circuit as input. You can do this very generally, and it's using this trick that's called uncomputation, which is also another quantum building block. It's an example of a quantum building block. You can always take a classical circuit computing Boolean function and convert it to a quantum circuit computing the Boolean function in this way. So when I say a quantum circuit computes a Boolean function, it means it implements this map. And the conversion has this nice property that if your classical circuit used some number of gates, let's say it used G gates, the quantum circuit will also use order G gates. So maybe it'll be a constant factor times more, maybe it'll be 5 times G gates or something. So this is how you take classical functions and bring them into the world of quantum algorithms, because a quantum algorithm is going to need a quantum implementation of a function of this type. Okay, so we assumed that the classical function was of polynomial size, therefore the quantum circuit for OF, the gate count is also going to be polynomial. Good, so this is the first step. We already used a building block, this trick called uncomputation. Okay, then recall Grover's algorithm from the previous slide. It says that if you have this ability to do OF, then Grover's algorithm will decide for you if f of x is 0 on all inputs, or if there's some input on which f of x is not 0. And its cost is square root of 2 to the n uses of this guy, this unitary OF, and this number of additional elementary gates. So obviously the second step is to apply Grover's algorithm on this object we constructed in step 1, and this is going to be the total gate cost, 2 to the n over 2 times some polynomial factor. So what I want to take away from this is already a quadratic speedup compared to the classical algorithm, right? So the best classical algorithm, the one I showed you on the previous slide, and it's widely believed that you cannot really do better, takes time 2 to the n. This takes 2 to the n over 2. So just forget about polynomial factors. It's not really relevant compared to the exponential factor up front. 2 to the n over 2 is it's 2 to the half n, right? And classically, it's believed that you can't even do 2 to the 0.999n. So this is a quadratic speedup over the best known classical algorithm for a concrete problem. Good. Okay, so why did we go over this example is probably what you're thinking. So let me answer that in a second. And let me also just say that Grover's algorithm, and more generally black box algorithms, so the question was, often assume some black box as input to to finally get an algorithm that works just to get a fully fleshed out circuit, you have to instantiate the black box, as in you have to replace the black box with the real circuit. So that's what we did over here. This part is often called instantiating the black box. So that's another terminology to be aware of. So, right, so you might be thinking like, why did we go over this example, right? So it's a pretty simple example. Maybe people have seen this before. It's just a basic use of Grover's algorithm. Well, one reason we went over the example is just to give you an example of the process I was describing earlier, right? You can upgrade a classical algorithm. We took a classical algorithm, it did a brute force search over all possible assignments, and we said, oh, let's replace the brute force part with Grover's algorithm, right? So, okay, that's an example of that method. But another reason I did this is because I wanted to refute a misconception that some people have, and I figured this is a good time to do it, which is that people think Grover's algorithm only provides speedups in this black box model. So the black box model is also called the oracle model. So when these oracles are involved, that's the only time you get speedups from Grover's algorithm. Grover's algorithm doesn't give you real speedups in the circuit model. Like, you know, this is a erroneous claim that I've heard before. So that is not correct, because the previous algorithm the previous example that we just did, at the end of the day gave you a quantum circuit that had gate count roughly 2 to the n over 2, whereas the best known classical circuits have gate count 2 to the n. So that's a legitimate speed up in the circuit model. Those circuits don't have any oracles inside them. There's no black boxes. It's just a fully fleshed out circuit. Okay, so if you've read this misconception before, this is not true. I've even seen papers that kind of talk about this. Anyway, okay, a second misconception that I also wanted to address by giving this example is that people think that Grover's algorithm needs something called QRAM, which is curious because like I haven't even talked about what that is so far. So how could it need an object that I haven't even introduced, right? So there's that's not a thing that you need for Grover's algorithm. That's certainly one way to do Grover's algorithm, to instantiate the black box. And I will talk about that. But you don't need that. So the previous example, no QRAM, if you know what that is. And if you don't know what QRAM is, I'm going to explain it in a couple slides. Good. So this was the reason I talked about this example. And so maybe you're thinking, well, what is this QRAM object? And I thought I'll take some time to talk about this in this tutorial because it's kind of a thing that's become more popular in recent times, I'd say, in the quantum algorithms community. It wasn't a topic that people talked about too much. And then, I don't know, I want to say like 5 years ago or something, people started talking about it more. And so it's kind of newish in a sense. The concept is not that new, but people have been talking about it more. And maybe if you haven't heard about it, I will take a few slides to explain what it is. But before getting to what it is, let me just give you a very high-level overview. It's a model of computing that's stronger than the circuit model. So we talked about the circuit model and what you can do. You can do these elementary gates and the total cost of the total number of gates. This is a different quantum computing model. It's more powerful, and it's also controversial. So some people really hate it. Some people love it. I won't get into why people hate it and love it. It's mostly because of reasons of like, can you implement this with actual hardware? So that's the kind of question. So, you know, even if you're just a theoretical computer scientist and you're like, you know, I study abstract things, you like to study things that actually model things that can be done in the real world. Right? That's kind of the motivating reason why we define certain concepts in theoretical computer science, because we think this will model actual computation. So people don't like this QRAM because some people think you cannot do this in the real world. There's no hardware that will support it. Some people do. So anyway, I won't talk about that. I'll just tell you what the mathematical definition is of QRAM. So it is a well-defined, mathematically well-defined concept to study. So certainly you can study it if you want to. It was originally proposed in this paper from 2008. And there's a recent survey of QRAM, but also a critique from just last year. So if you're interested in more about this controversial aspect of it, I'd suggest looking at this last survey and critique. I'm just going to tell you the mathematical definitions and not get into controversy. If you end up having dinner with an algorithms researcher or a hardware person, feel free to ask them what their views are on QRAM, and you might have an interesting conversation. Okay, good. So that's that, and I'm going to tell you a little bit about random access models. It's a bit of a detour, but I figured it's an important detour to take. And before doing that, let me take questions. There's a question over there.
Hello. I wonder if the previous slide, I'm wondering if the classical and the quantum algorithms are being compared in the same footing, because in Grover there's an assumption of the oracle existing, but knowing the oracle is not in general is not an easy task.
Oh, no. That's the exact reason I went over the example, is because I instantiated the oracle. I didn't assume it existed. This oracle can be made out of the input that you're given, the classical circuit, using this primitive called uncomputation. I didn't get into that. So this is you can find this in the early pages of Nielsen and
But the
Chuang.
unitary itself, this is the action of the unitary, but the exact circuit is not necessarily easy.
No, it is. That's my claim. I'm not showing it to you because I assume people would know this, but
Okay.
you can always do this. So if you give me a classical circuit for F, I can create a quantum circuit for OF, the object that's listed over there, and it'll have the same gate complexity up to constants. So if the classical one uses G gates, this will use ordered G gates. Maybe it's 5G or something. I don't know what the constants are.
Okay.
Yeah, this can always be done. This is a very important takeaway message, so yeah. Thanks for the question. You can always do this. This is very important. If you couldn't always do this, then this would be kind of bogus, right? Like we're just assuming we're doing an apples to oranges comparison, as you were pointing out. Yeah, there's a question there, and there's a question
there. Is there any possibility that quantum oracle is in fact efficiently simulated by classical computers? I mean, if you have a G gate to make some classical circuit, and of course you can make order of G quantum gates to make the circuit, but there might be some different classical techniques that can efficiently simulate the kind of quantum oracle.
What does that mean? We already have a way of computing the function classically, right? That's where we started from, and from that we came to a quantum oracle that does the what I would call the quantum version of that function. But if you just want to simulate this classically, you already have that, right? That's what you started out with.
Yes, what I mean is that is it possible there might be more efficient way
to make this out of the classical circuit?
Yeah.
Oh, yeah. Oh, right, that's a good question. So what I said was like, if your function f is computed by G gates, then a quantum oracle can always be done with ordered G gates, but it could be done with less than ordered G gates. Yeah, that's certainly possible. It's not generically possible. Like I can't tell you for every function how to do it with fewer than that number. In fact, that's not possible because there are some functions you cannot do it. But for some functions you would be able to, right? Like for example, if the function f is a function for which there are just better quantum algorithms for computing that function, like factoring, let's say. If f was literally doing factoring, classically it would be like some exponential time circuit, and if you wanted to do it quantumly, you would have a n cubed time circuit, or whatever Shor's algorithm's complexity is. So there would be some functions which you could do faster on a quantum computer, but generally now. There's a question there, yeah.
So also about this uncomputation building block, is there some constructive way that actually describes how to do it? Or is it just like, I change everything to NAND gates and then I implement them with Tofoli's and things like that?
Wait, what do you mean constructive? Isn't that's constructive, right? Your original classical circuit was built out of AND or NOT gates. You replace every AND and OR gate with a Toffoli gate. You replace negation gates with a Pauli X. You add some ancillas because quantum circuits have to be reversible. Then you do this uncomputation trick to get rid of garbage. And so it'll give you an explicit circuit. So like I could write down a computer program that takes in as input a circuit for the original function f, a classical circuit, and outputs a quantum circuit for OF, like as an explicit quantum circuit, like just every gate by gate level of detail. So this you can do fully explicitly, and it's very straightforward. Yeah.
So that's the way you would actually do it. If you had maybe with AND and OR gates, I can understand. But if I have, I don't know, a Python function which I can then map into, but it has for loops and it has while loops and stuff like that. So it's not very trivial to map it all the way down to NAND gates. How would I actually implement this uncomputation step?
Right, good question. Right, so what if you have an algorithm in a different model, which is not the circuit model, classically? So what you can do is, first convert it as a circuit model. And generally, this part we don't talk about so much in classical computer science because people just like Python code or whatever. But generically, you can always convert this into a circuit, and the circuit will have the same size as the running time of your original algorithm. I will actually get to this a little later in the talk, but even classically, there's different computational models that people study. People don't just study circuits, right? So of course, people study code in Python, for example. Some of them can be converted to circuits with no overhead whatsoever. Sometimes you can't, but I'll get to that. But let me put it this way: if you do write Python code for some function, almost certainly you will be able to get a circuit out of it in a completely generic way, in some kind of black box transformation way, like with no ingenuity required, just some very mechanical way that'll have the same circuit size as the running time of your Python code. Good. Okay, let's take one last question.
I was curious, is there any connection to functional programming or thoughts of functional programming in this? This black box point of view makes me kind of think about it with my limited understanding of this kind of paradigm of
Yes,
programming.
that is a good question. Yes, I wish I had a better answer to that. I am also not an expert on functional programming, but I do know they love functions and expressing stuff as functions of functions and so on. Yeah, off the top of my head, I can't say if there's a direct connection between black box models and functional programming, but there might be. So
Okay,
good
thanks.
thought. Okay, cool. So we went over this example, and then we started talking about random access models. And let me talk more about this question. It's a good segue into the next topic, which is classical code in other computational models that are not the circuit model. How do you convert them to the circuit model, and is there an overhead and so on? And to talk about this, I'm going to have to talk about random access models. So it's a bit of a detour, but hopefully people will find it worthwhile. At least one person who asked the question will find it worthwhile. It'll also answer the question of what is QRAM. So okay, so yeah, so let's get straight to the heart of this question. So when a classical person says that the time complexity of a classical algorithm is something, right? So you've probably heard this phrase many times, like, oh, this algorithm has time complexity n cubed. So just as a concrete example, someone might say, oh, you can multiply n by n matrices faster than n cubed time. N cubed time would be the trivial way of multiplying two n by n matrices, just like the way you were taught in high school to multiply matrices. You can actually do it faster. You can do it in this time. This log 2 to the base 7 is like 2.81 or something. It's less than 3. And this algorithm is a famous classical algorithm called Strasson's algorithm. It's constructed using the divide and conquer paradigm. Okay, so people will say this. So what do they mean? What does it mean to have time complexity, this thing? So if even if you've taken a classical algorithms course before, you might not really have thought deeply about this question. Like, what does this actually mean? So let me give you 4 options of what this might refer to. So this might refer to the circuit model. It might mean that this function, this matrix multiplication function, which is like I'll take in as input 2 matrices, output another matrix, requires a total number of and or not gates that is this number. That's option 1. Option 2 is they're actually not talking about circuits at all, talking about Turing machines. Turing machines are these popular computational models in computer science, right? If you've taken a intro to complexity theory course or talk about NP completeness, we love Turing machines. We talk about them all the time, and we talk about running times on Turing machines. So maybe that's what they mean. Or maybe they're talking about some kind of random access machine. This is closer to the question about Python code, because so I haven't told you what a random access machine is, but let me say just briefly, in a random access machine, what happens is if you want to look something up in memory, so you want to randomly access memory, you can do this really fast, just like you would expect if you're looking up the nth element of an array in Python. Like, you don't expect it to take a long time. You expect to just look it up instantly. So this is maybe more analogous to what you might expect for programming language running time. And maybe the 4th option is the depth of a classical circuit. So, a classical circuit has a total number of gates, but it also has a depth, which is just how it has a width and depth. Maybe let's do an audience poll just for fun. What do people think when a classical computer scientist says, you can do matrix multiplications this time, or whatever your favorite algorithm? You can do a graph algorithm, all pair shortest paths, or Dijkstra's algorithm in some amount of time. What are they talking about? So, okay, how do we do this poll? How many people think it's 1? Show of hands. Okay, some people. How many people think it's 2 Turing machine time? Okay, maybe more people. How many people think it's random access machines? Oh, even more people. And how many people think it's depth of a classical circuit? Some people. Oh, good. Okay, we kind of have an even distribution. This is excellent. Yeah. Oh, thank you so much for taking part in this audience poll. We'll have more audience polls later. You've been a fantastic audience, indulging me with this poll. So, okay, let me tell you. Okay, firstly, it's not totally clear. Like, they could mean multiple things. So there's not necessarily a definitive answer, except one answer is wrong, which is 4. 4 is wrong. Sorry for all the people who said 4. Because the depth of a classical circuit computing a function can often just be exponentially smaller than its total number of gates. So for example, for this matrix multiplication question, there's a question of, do you multiply matrices in n cubed time, or n to the 2.8 time, or n to the 2.6 time, and whatever. But if you just care about the depth is log n. So log n is exponentially smaller than n to the whatever. So this is almost never what anyone means when they say time complexity. Sometimes people will say things like parallel time to refer to the depth of the circuit, but when they just say time complexity, no qualification, it's never the depth of a classical circuit. Okay, so it's one of the first 3. Now, the nice thing is that 1 and 2 are basically the same up to log factor. So those of you who said 1 and those of you who said 2, you said basically the same thing. So it doesn't matter. Up to log factors is the same thing. It's just a matter of taste. Do you like multi-tape Turing machines better? Do you like circuits better? The quantum computing audience definitely loves circuits better. We never talk about Turing machines in quantum computing, right? Doesn't anyone even know the definition of a quantum Turing machine? Like, that's some absolutely insane object. So, okay, so 1 and 2 are the same, and I'll tell you a little bit more about 3. And before we get to that, I think I saw a hand go up. Somebody wanted to ask a question? No, okay, good. Right, so 1 and 2 are the same. 3 is different, and I'll talk about 3. Yeah, 1 is circuits. We've been talking about circuits so far, so everybody knows what that is, hopefully. And 2, I won't explain because 2 is the same as 1, so I won't explain what Turing machines are. Let's not even go there. So let's talk about random access machines. And let's talk about why do people like random access machines? Why do people come up with random access machines? And that's because circuits and Turing machines have one simple problem. And this problem is looking stuff up in memory is really time-consuming on circuits or Turing machines. So let's take an example. You have m bits stored in memory, z1 through zm. So you ran your algorithm. During the course of your algorithm, you stored stuff in an array. The array has length m. Maybe you're writing code in Python or whatever. And now at some point, you want to look something up. You want to look up what's stored at position y. So y is a number between 1 and m. It's the length of the array. And you want to look up what's stored at z sub y. Seems like a totally reasonable thing to do, right? Of course, when you write code, you do this all the time. This takes a long time on Turing machines or circuits, which is very unfortunate. So in fact, on a Turing machine, worst case, this will take something like order m time, the size of the memory, because Turing machines are a sequential access model. So if you're reading memory at, let's say, position 1, and then somebody asks you, hey, what's stored at m, you have to move your tape head one step at a time, and each movement takes one unit time. So this will take linear time in the size of the memory. So this is pretty terrible. And a circuit also has the same problem, and let me demonstrate what I mean by this. So let's say you have a circuit. It has 2 types of inputs. First is the memory. This is a bit string of length m. And then the second part is the address, y, which is a number between 1 and m, which is a bit string of length log m. And I want a circuit that takes in these m plus log m bits of input and outputs 1 bit, which is what is the bit stored at position y in my memory z. This function is also often called the address function. Any circuit for this function will require at least m gates. That's what I'm claiming. And if you want to see why that's the case, so if you have less than order m gates, if you have little o of m gates, then there are some memory wires that have no gate acting on it, right? Because there's m memory wires. And if you have less than m gates, like you have m over 100 gates, some memory wires just like keep going through and have no gate acting on them. So there's no possible way information from that wire could travel to this guy if there's just no gate acting on it. So you can't have a circuit with fewer than m gates computing this address function. So, and as I said before, this Turing machine model and circuit model are basically the same. So if it needs linear time in the Turing machine model, it's going to need linear time in the circuit model because they're basically the same thing. So this is the reason people invented random access, because this is kind of annoying. You can't look stuff up fast. So what do? You just define a new computational model. We'll call it the random access model. And in the random access model, this operation, instead of taking linear time, we'll just say it costs log m time. Right? So I'm just giving you a mathematical definition right now. I'm not saying you can build this in the real world. This is just a nice, well-defined computational model where I say, every time you want to do this operation, look stuff up in memory, it only takes log m time instead of taking m time that it would in these other models that we know and love. So that's just, I just defined it that way. So by definition, you can solve this problem in a RAM model exponentially faster than you can solve with a Turing machine or circuit, right? So that's just by definition. We just constructed the RAM model to have this property. That's not an interesting insight about the RAM model. That's just how we started out. So you can always get this exponential speed up for this specific task if your random access memory, like the thing that you're able to make this random access to, has these bits stored in it. So I'll say a little bit more about that, but maybe I should pause here. This is maybe the first part of the talk that might be confusing, especially if you've never seen random access machines before. This might be a little confusing. Questions? No, okay. So, right, so random access models, very nice. They solve this problem of looking stuff up being painful. There's many definitions. I don't want to get into any of them for classical random access machines because that's not how we define quantum random access machines. You can have definitions through Turing machines, through register machines, through something called word RAM. That's just like all over the place. So let me not get into that, but let me just give you some takeaway message about what's going on with the classical RAM model. So classically, if your RAM model, if you have some problem where like there's some input stored in RAM, like on the previous slide, you had this array stored in RAM, and you have some question like look something up, that can be solved exponentially faster in the RAM model versus circuits or Turing machines. So there's an exponential gap if stuff is stored in RAM before you start your problem. On the other hand, you can also study random access models where you say that nothing's allowed to be stored in RAM before you start. The RAM is empty. So it's like you just turn on your computer and your RAM is empty. It doesn't have anything in it. If you want to, and your input to your problem is given to you in non-random access memory, just in sequential memory, let's say the tape of a Turing machine or your input bits of a circuit, you can copy it to RAM if you want, but then it'll take time, right? To copy one bit of memory stuff to RAM, it takes at least log m time. So if you work in this kind of setting where your input is not stored in RAM and your RAM starts out completely empty, then you don't get any exponential speedups anymore. You can at best have a quadratic speedup. And this was shown in this very old paper, at least with my definition of RAM. There's like many different definitions of RAM, as I was saying earlier, and they can get kind of complicated. But the way I define it, where looking stuff up in random access memory takes log m time, I'd say that's the reasonable definition. And if you use this reasonable definition, at best you can have a quadratic gap between RAMs and Turing machines. And what I mean by that is any algorithm that takes time t in the RAM model can be simulated to a circuit or a Turing machine with time t squared. This is just the pessimistic worst case upper bound. In practice, it's almost always linear. So if you have an algorithm in the RAM model that takes time t, you will generally be able to come up with a circuit or Turing machine that takes time t with some log factors. So this is answering the question earlier about like, what if I had some code in Python? Generally, if you're analyzing Python code, you're thinking about the RAM model implicitly. Whether or not you think about it, like whether or not you've thought about this very formally, you're thinking about looking stuff up in arrays as being a cheap operation, not as being an expensive operation in Python. So if you just naively applied this theorem, like this, which is the best worst case guarantee that I know, you might say that the circuit would be quadratically worse, but in practice, it doesn't happen to be that way. Generally, you will come up with a linear time circuit, or the same time circuit, or Turing machine. But okay, so this is just classical stuff. This is not quantum yet, but I just wanted to give you like the lay of the land of what's going on classically before we get into even more complicated stuff of like quantum, because now there's going to be crazier stuff going on, because obviously there is, because it's quantum. There's a question? Yeah.
So the circuit model argument you gave for why it takes omega of n to do random access seems to represent like physical reality of how chips look like. Like a 2D CMOS chip kind of looks like that. Doesn't this suggest that classical RAM is unphysical and therefore impossible?
Yeah, very good question. So yes, so this is part of this debate of controversy of why QRAM is like, people are like, oh, this doesn't make any sense, and like, yeah, why would it be possible to do this, and like it violates special relativity and so on. Let me not get into that. Let me just say that I think the consensus in classical computer science is that RAM is a reasonable way of modeling existing computers that we have, like the laptop that I made these slides on and the desktop that you have at home. At least the RAM portion of it, not your hard drive, the RAM portion of it. You really can look stuff up fast. And yeah, it's true that like you might say that, is this really, it's one of these things where it's like, is this, we made a mathematical definition. Does this capture reality? I'd say people think the answer is yes, classically, but that's because these objects exist, because we have this RAM, because you can just go to the store and buy, whatever, how much RAM do I have? 32 gigabytes of RAM from some company, Kingston or whatever. You just, it's just available. And it's available and it really does work fast. And so it's kind of like the proof is in the pudding kind of argument where it's like, this models reality well because you can do it. The problem with quantum RAM is that people would say that that just can't be built and we don't have the analogous, like what would the architecture be and so on. So anyway, very interesting questions, but also very contentious and controversial. And I don't want to get into that. Any other questions? Good, okay. So so this is a summary of classical stuff, right? So classically, so TLDR, if you don't care about classical stuff, here's the summary. There's two models you should care about. Circuits, which is the same as Turing machines. So if you don't like Turing machines, forget about Turing machines. There's circuits, and there's random access machines. If you're talking about problems where the input is stored in RAM, you can have an exponential gap between the two. If you're talking about problems where the RAM starts out empty, you can at best have a quadratic gap. In practice, it's actually more like linear. this is why classical algorithms papers will often not even mention what the algorithmic model is. You'll read a classical algorithms paper and it'll just be like, oh, it runs in whatever this time. What's the model? And it's because, well, it's probably the RAM model. That's probably what they mean. If you worked really hard, you could probably make it work as a circuit. But people probably don't want to do that part. It'll be very annoying. And because in practice it generally ends up being linear, people won't talk about it. Okay, this is classical stuff. Now let me get to quantum. So I wanted to do the classical stuff first because it helps understand some basic concepts like this exponential gap and what random access means, because quantum's going to make everything a little more complicated, because it does. Okay, this is the takeaway I just said. So let's talk about quantum. So before defining the quantum random access model, let me try to define a classical model that is defined in the way we define quantum random access. So classically, people don't define random access using circuits. Classically, people prefer other things. But let me just do it with circuits, because this will straightforwardly generalize to quantum. Right? So what would a random access model look like with circuits? So with a circuit, what you do, you'd have two types of memory. So first, we'd have this special memory that you have random access to. This is the part that we called previously Z1 through Zm. This is the RAM part of the memory. And then I'm also going to have other memory, which you don't have random access to. The special thing about this memory is the only way you can talk to this memory is through this RAM lookup. You can only read something or write something to this memory through this random access gate. And what does that do? A read operation will take in an address, a y, which is a number between 1 and m, and it'll go and read what's written at that position in memory, and it'll tell you what it is. A write operation will do kind of the opposite. It'll take some bit b, it'll go to that location in memory, and it'll write it. And this is the only way in which you can access that memory. And what I mean by that is you cannot do logic gates on that memory. You cannot be like, oh, I'm going to go there and put a NOT gate, or I'm going to go there and do an AND. That's not allowed. You can only do these random access gates. And then you have other part of your memory, because you also want to do logic gates. You want to do AND, OR, and NOT if this is a classical circuit, right? That, we love doing that in classical circuits. So yeah, so let me combine this read and write operation into one operation here. And actually, let me show you a picture of let me show you the picture first. So this is what's going on. There's this special memory I'm calling Z. You can only interact with it through this random access gate, the one that either lets you write or read stuff from memory. You cannot do basic elementary gates on it. And then there's standard memory, where you can do all these black boxes are supposed to represent AND, OR, NOT gates, or whatever your elementary gate set is for classical computation. Okay, so what is this random access gate? I just combined the read and write operation into one gate, just for convenience. You can make them two separate gates, but let's just make it one gate. It'll be nice. And what it does is, first you specify the address, then you specify a bit, and this is the memory, the special memory part. And what it does is, this address says which bit I'm looking at. So let's say I'm looking at ZY. And what it does is it swaps this bit B from my memory into the special memory. So how do you use this to read data? It's kind of clear. Like, it took something that was stored in special memory, it transferred it to my memory. So my memory is, the standard memory is the first log n plus 1 bits. So now I have this stuff. I can go do whatever I want with it. And how do I use this operation to write stuff, which is also kind of clear. Like, B is the thing that I'm writing to location ZY because it got swapped. So B went over there. The advantage of having just one gate is this is a reversible gate, in the sense that if you do this gate twice, you'll get back to the original situation. So because it's just swapping two things, if you do it twice, it swaps them back. So it's reversible, which means it's unitary. So this means I can quantize this gate. I can come up with a quantum analog of this. And that's kind of why I wanted to think of it this way. Okay, so this is how one would define a classical circuit with a random access gate. As I said before, people don't do this because classically people don't use circuits for defining RAM. But if one had to, this would be a reasonable way of doing it, I think. And this is how it's done quantumly. Okay, so now finally let's come to quantum RAM. And unfortunately in quantum RAM, there's two types of quantum RAM. So this complication did not exist classically. There was just classical RAM, and then there was circuits. Quantumly, there's two notions of RAM, and sadly both are called QRAM, which is very unfortunate. Very unfortunate. And I'm going to give them different names for this talk because it's going to be crazy if I keep calling two different things by the same name. So the first one I'm going to call CQRAM, or QRACM, which stands for Quantum Random Access Classical Memory. And now the name gives it away. The memory is classical. Even though we're talking about quantum algorithms, the memory can only store classical data. That's what's special about this memory. So here the memory stores classical bits, and you can only read in quantum superposition. So if the memory is classical and you can also only read and write to it classically, then that's just classical RAM. There's no quantum going on. So something has to be quantum. The part that's quantum is you can read in superposition. So you can, the register that said, what the address was, these log n bits, this register can be in superposition. The second register cannot. That's not in your control. The memory is just what the memory is, but you can read in superposition, and you'll get you'll get this B thing back in superposition. So that's what I'm going to call CQRAM. It's going to be easier than saying QRACM. So that's what's going on in CQRAM. You have some classical data that you stored in random access memory, and your quantum algorithm needs random access to it. That's why we like CQRAM. On the other hand, if you want to do something totally analogous to the previous thing, which is you want to have both quantum read and write access, you can just define the quantum analog of the gate I had on the previous slide, which is, you can call it a quantum random access gate. It's just the previous gate, but now I put ket signs on it because it's a quantum gate. So here you can both read and write in quantum superposition. So this I'm going to call QRAM for quantum random access memory, or QRAQM for the fact that the memory itself is quantum. So just in case you're confused, what's the difference between these two? Just the question to ask yourself is the memory storing classical bits, or is the memory storing quantum bits? The access model is quantum, so forget about the access part, but just what is the memory storing? Is it storing bits, or is it storing qubits? In other words, can the memory itself at some point become entangled with the algorithm, or is that not a meaningful sentence because the memory is just storing bits? Or otherwise, at any point in the quantum algorithm, can you just pause and be like, hey, what's stored in quantum memory? If the memory is classical, then of course you can ask this question. If the memory is quantum and it's entangled with the algorithm, then you might not be allowed to ask this question, at least in the Copenhagen interpretation, right? Like that's now entangled with the quantum algorithm. I cannot answer meaningfully what's stored in memory. So that's the difference between these two models. Unfortunately, not all papers are very clear about which model they're talking about. Sometimes they are. And let me give you some examples of, before that actually, actually let me pause here because this is a bit of a heavy topic. Anyone have any questions? There's one question in the back.
How do you define the right
very good question.
operation for the classical one?
Right.
Or are you just measuring the memory all the time?
So you have to be clear about what you mean in your algorithm. Some algorithms that use CQRAM, actually, the way they work is there's some classical phase of the algorithm that's just totally classical. They write something in RAM. There's no quantum algorithm going on this part. So just write something in RAM, and then your quantum algorithm starts. Once your quantum algorithm starts, no writes are ever performed. That's one way to think it's done. Sometimes you might have both, and then I haven't seen this totally rigorously written down somewhere, but I'd say the correct way to do it is like whenever you want to do a classical write, you should measure your quantum circuit, and you should have no quantum computation going on. So let's say you measure everything out, the quantum computation is ceased, your classical controller or whatever writes to memory, and then you can restart your quantum algorithm. Maybe that's fine. That would be one way of doing it. Cool. Yeah, okay. Let's, right, so let's ask the same question we asked before, which is, can you get a speed up in the RAM model versus the standard circuit model, right? We asked this question classically, and we talked about two scenarios. If your input itself was stored in RAM, then you could get this exponential speed up, and otherwise you could only get a quadratic speed up. The first part is the same here, right? If your input is stored in this memory, and your task is to just look the thing up, like to compute this address function, then of course you're going to get an exponential speed up in this model versus quantum circuits. That's how we defined the model. That was the whole motivation for defining the model, that this address function took too long. So this is completely unsurprising that you get an exponential speed up, right? So, okay, so this should be clear. It's the same story as classically, nothing's going on, that's quantum here. The second question is, I think, the more interesting one, which is that what happens if you don't have the input stored in RAM? Your quantum RAM has to start out empty. So here I think, but I haven't seen this formally written down with like a fully rigorous proof, so I don't want to say this is necessarily true. But I think from the results of this paper, you can actually simulate any quantum RAM, whether it's CQRAM, QQRAM, doesn't matter, algorithm in the standard circuit model with only a polynomial blowup. And in fact, I think the polynomial blowup is only quadratic, just like in the classical simulation, as long as your quantum algorithm is only using a reasonable amount of memory. So by reasonable, I just mean polynomial. So like you don't use, if the running time of your algorithm is t, don't use 2 to the t memory. Like that's absurd. Like why would you need exponentially more memory than the amount of time of your algorithm? So as long as that's not going on, I think actually this works. But this part, not totally rigorous because I haven't seen it written down anywhere. I haven't proved it formally myself. But I think the story is basically the same, that if your input's not stored in QRAM before you start, you can't get more than a polynomial speed up. And in fact, I don't think you can get more than a quadratic speed up. But unlike the classical case, there are examples where you do get some speed up more than linear, and I don't know how to remove the RAM, so to speak. Unlike classically, where I was saying that if you have something that runs in the RAM model, it basically will work in the circuit model at the same time. That's not true quantumly, at least as far as I know. Yeah, okay. And maybe as my last thing I wanted to say is that, okay, yeah, maybe you're thinking like, where is this QRAM used? What quantum algorithms use QRAM, and which ones use CQRAM, and which ones use QQRAM? So I just wanted to give you some examples. Yeah, maybe I won't go through these, but these are three well-known algorithms, all previously presented at QIP, that use CQRAM. These are some examples of algorithms that use QQRAM. Yeah, that's okay. Not going to say much more about this. Yeah, what do I want to end with? I just wanted to end with, okay, is my clicker working? Yeah, navigating the quantum algorithms literature. As I said, people are not always totally clear about whether they're using QRAM or not, which is kind of sad. Sometimes you'll find this on like page number 23 or something, saying that, oh, actually we're working the QQRAM model, or they won't even, whatever. That's kind of sad. So tip for readers, if the paper uses the term gate complexity, it's just like a rule of thumb, like it's not a theorem or anything. They probably are talking about the circuit model. If they use time complexity, they might be talking about RAM, but they could also be talking about the circuit model, because recall classically, Turing machine time is the same as circuit cost. So time could mean both things. So this is why it's unfortunate. It's not very clear. But it is what it is. Hopefully those of you in this audience now who've watched this tutorial will, next time when you write a quantum algorithms paper, be clear about your computational model. Good, let's do a quiz just to see if people understood what was going on. This quiz is related to the stuff we talked about, random access models and so on. And it's also related to Grover's algorithm, which we also talked about. So it combines everything I've talked about so far in my talk. Yeah, let's do this quiz. Cool. So here's the question. This is the problem. I have n input wires that are some n-bit string, x1 through xn. These are all classical basis states for some classical string x. I want to decide if x is the all zero string or it's not the all zero string. All right, so this should hopefully remind you of Grover's algorithm, because that's kind of also what's going on in Grover's algorithm, except the access model is a little different. Right? So in Grover's algorithm, you have this black box and stuff. There's none of that. There's just n incoming wires to your circuit that have bits on them. Classical basis states. You have to decide if it's all zeros or one of them is not zero. So, and the question is going to be, how much time does this take? Or let's be more precise. In the standard circuit model that I introduced, so the complexity measure is how many gates do you use? How many gates do you think you need to solve this problem? And let me narrow down the choices. Even classically, so no quantum algorithm, even classically you can do this with order n gates, or maybe up to log factors order n. But let's say, in this talk I'm not really quibbling over log factors. So there's n gate algorithms even classically. The question is, can you do this better quantumly? And the only other logical choice would be root n because of Grover's algorithm. So these would be the two options. So let's do an audience poll because we had so much fun last time. So what is the gate complexity of this problem in the quantum circuit model? The two options are n and root n, up to log factors. So how many people think it's n? Raise your hands. Okay, quite a few. How many people think it's root n? Okay, yeah, also, I think I want to say less, I want to say, yeah, more people said it's n than root n. And n is the correct answer. So those of you who said n, give yourself a round of applause. It is n, and actually it's the same argument as before for why RAM doesn't make sense. Like you cannot do RAM in the circuit model, because if you had, if all of these were 0, but just one wire was 1, and all your gates are, either a 1-qubit gate or a 2-qubit gate. If you have less than n gates, then there are some wires that don't even have gates touching it. So how could this final wire even know of the existence of that bit being 0 or 1? Right? If all the other bits were 0 and that was the only bit that was 1, you couldn't carry that information through. So here the answer is n. Okay, let's make the problem even harder now. Now let's go to either the CQRAM or QQRAM model, doesn't matter which one. And these bits are stored in the special memory, the one that you do have random access to. Same question, can you do this with now cost n or root n? So let's, how many people think it's n? Show of hands. No one thinks it's n? Yeah. And how many people think it's, how many people think it's root n now when you have this data stored in your special memory? Okay, far more people think it's root n. And yes, that is correct. You can do this with root n, because now you can use Grover's algorithm and you can instantiate the black box, the part that said go look something up, with this QRAM gate, this QRAG gate that you were given, right? So that's good. And finally, what if you're in this QRAM model, but the memory starts out empty? That means these bits are not stored in the special memory that you have random access to. They're just stored in your regular memory. If you want to copy it to QRAM, you can, of course, but that takes time. Now do you think it's n or root n? So how many people think it's n? Okay, a lot of people. How many people think it's root n? No one. Okay, good. So that was the correct answer. It is n indeed. You can't do that. Good. So that means everybody totally followed the last, I don't know, couple sections of my talk. And we're almost at time. This is also the, I was going to get to the, it's probably better to stop here. Okay, so let me take questions and let me stop here because we're almost at time. And thanks for coming to the first half of this tutorial. I will now take questions. Please come back for the second half.